Hi, in this video we're going to talk about data types, which I'll be honest is not the most thrilling topic that we're going to be talking about in this course, so I want to motivate this with an example about why you should care about data types. We're going to give a pretty realistic example with a fake data set. The data that we're working with is called cat lovers, and let's suppose that it comes from a survey that asked respondents their name and the number of cats. And the instructions said to enter the number of cats as a numerical value. So for example, Bernice Warren took the survey and they said they had 0 cats versus Willie Bass took the survey and they said they had 1 cat. There's also a handedness variable where we ask the survey takers whether they use their left or their right hand or if they're ambidextrous, but we'll get to that later in the video. Okay, so the first thing that we might want to do is to think about what's the average number of cats of these survey takers? So we had 60 people who responded to our survey. So I might say something like, let's start with the cat lovers data frame. And then we're going to use the summarize function to calculate the mean number of cats. So the mean score that I'm going to calculate, I'm giving it the name mean cats, and I'm using the mean function to find the mean of the column called number of cats. That's what the column was called in our data frame. I get an NA and I get a warning saying argument is not numeric or logical, returning NA. So maybe my next move is going to be to take a look at the help file for mean. And I see something about NAs in there. We've seen this earlier as well, where it says that the mean function has an argument called na.rm, which is a logical value. So it takes a true or a false for indicating whether NA values should be stripped before the computation proceeds. So maybe if somebody hasn't responded to that question on the survey, their value might be recorded as NA, and hence maybe that's the reason why we can't calculate the mean. So let's give it a try. I can add the NARM argument, setting it equal to true, but it still doesn't work. So what might be going on here? Let's take a breath and look at our data. I'm going to use the glimpse function to take a look at my data set, and let's think about what is the type of the number of cats variable. So number of cats here is recorded as character, but we said we asked people to put in numbers, and in fact I am seeing numbers here, so it's a little bit bizarre why it is saved as a character, which I can also tell by the fact that these values are actually stored in quotation marks. Let's take another look at our data, and this time I'm actually going to drill down and take a look at the entire data set, which you might be thinking, hey, you only have 60 people, that might feel easy enough. What if you had 1 million? And you're right, that as the data set size grows, this sort of inspection is hard, but so is data cleaning. There are other methods other than just taking a look at the raw data when you have larger and larger data sets, but sometimes some of this is going to feel a little bit tedious. So all of these people have given numbers. I'm going to keep scrolling through to see what might be going on. Ginger says 1.5. Honestly, I think one of my cats is half human. Now, I know where Ginger's coming from, but we asked people to give us numbers, and this is what they put in for the survey. Another one is Doug, who actually just wrote the number 3, even though the survey instructions asked them to put in numerical values. Doug decided, oh, I'm special, I'm going to type out my answer. So what is happening here is that because we have these 2 character strings, the character string that comes from Doug's answer and the character string that comes from Ginger's answer that don't look like numbers, that are character strings, R basically decides we're going to have to make this entire column a character string because you can't, within a given variable, have different data types. So what we are going to need to do is we're actually going to need to fix up their answers. So let me walk you through how we fix it up first, and then we can talk about how we could have done better from the beginning. So what I'm going to do is I'm going to mutate my data frame because I want to basically change a column. This time, instead of adding a new column, I am changing a column. And I am going to change my column called number of cats. And the way I'm going to do this is using a case when statement. And you can think about a case when statement as an if or an if else statement on steroids. So basically what we want to say, if we were writing out our code in English, is to say, for Ginger, just make her number 2. For Doug, make his number 3, and everybody else should stay exactly the same. That's what we're trying to accomplish. So if I were to write this as if statements, I would say, if the name is Ginger, do this. Otherwise, if the name is Doug, do this. Otherwise, do leave things alone. So a case when statement allows you to give these logical sentences, checking for is it Ginger or is it Doug or is it somebody else, in a structure that appears the same for each one of your checks. So the way it works is case when is a function, and this function basically can take on as many arguments as you like, separated by commas, and each of these arguments is basically a condition and what should happen when that condition holds true. First we give the condition, and then we separate it by a tilde, and then we give it what should happen if that condition is true. So the number of cats variable should be constructed according to the following case when statements. If name is equal to Ginger Clark, make number of cats equal to 2. Remember she said 1.5, saying one of them was half human, so that's 2. If name is equal to, so we're using the double equals for checking again, Doug Bass, make number of cats equal to the number 3. For everything else, leave things alone, but convert them to numeric data. So this as numeric function is new, and it is about data types, and we're going to give you a little bit more context about that in a little bit. But basically, remember the rest of the data were also in quotation marks, even though people had entered the data in as numbers. Upon reading it into R, because of Ginger's and Doug's responses that were character strings, they were all converted to character strings. So now we're telling R, undo what you did. I'm now giving you numbers for these 2 people who didn't follow instructions. The rest of the people who did follow instructions, let's convert their answers to numeric data. And once we do that, we can again run our same summarized statement to calculate the mean number of cats. So here, the problem is that so the calculation works, but we are still getting a warning. So it says problem with mutate, input number of cats. It says NA is introduced by coercion. Okay. Input number of cats is case when. Okay. So yes, I am trying to calculate number of cats using a case when statement. But why is it actually still giving me a warning, even though it gives me a result that seems somewhat reasonable, average number of cats being 0.833? The reason for that is that these operations are happening sequentially. So in order to get rid of that warning, I can actually be a little bit more principled and respect the data types. Remember that when we loaded the cat lovers data set, that number of cats variable was a character string. So what I can do is when I fix up the entries for Ginger and Doug, I can also give them character strings. So I'm putting the 2 and the 3 in quotation marks. And then I say for everybody else, leave number of cats alone. So now I have a vector or a column called number of cats where every single entry is actually looks like a number to the human eye, but stored as a character string. And then all together, I convert all of them to numeric data. So I'm respecting the data type as I'm doing my fixes to my data and sticking with the same type that was given to me. And then once I have a column that I know can be converted to numeric data, I am then doing the conversion. So now that warning goes away and the value is the same. So a warning is not an error in R. A warning just says, hey, I'm doing something. You may want to be aware of this. You may or may not like what I'm doing. You may want to inspect and try to get rid of that warning, but it is not like an error where you can't trust any of the output. So we've learned about two things here. Well, actually three things really. One is that when you have in a given column in your data that you're reading in, variables that are of a mixed type, R will actually convert them all to be the same type. So that's what we call type coercion. And it basically converted all of them to character strings because just a couple of them were character strings. That's one thing. Then what we know is that we can actually fix up our data to fix any of these data errors. Let's call them data entry errors. And for that, we learned a new function called case when that we use commonly in conjunction with a mutate statement that allows us to write these logical statements and what should happen when those logical statements hold true. So in case when, we have the condition, and then a tilde, and then what should happen when that condition holds true. And I want to draw your attention to the last line of this case when statement now. I just left it as true. What that basically means is that if name is Ginger Clark, do what I said in the first line. If it's Doug Bass, do what I said in the second line. For everything else, so for all the other names, those first two conditions would have failed. And I'm saying for all of those other ones, act as though some condition has passed so that I don't have to string along all the other possible names, or I don't have to write an additional statement like if it's neither Ginger nor Doug. I'm just saying for everybody else, so that's what where the true comes in, leave number of cats as is. That's storing the old value of that column. So now that we know what we're doing, now that we know how to fix up this data set, we actually might then resave the data. And I'm going to just save it with the same name because I know that whatever I had to begin with, I did not want that at all. I want the correct data set. So I'm going to save over my data set with the assignment operator so that going forward, when I refer to the cat lovers data set, I actually can use the number of cats variable properly stored with numerical data. The moral of the story is that if your data does not behave the way you expect it to, type coercion upon reading the data in might be the reason. So type coercion meaning that you had some numeric and some character data, and R decided, well, I don't know how to convert all of this to numeric because I don't know what that sentence Ginger wrote means. So I'm going to convert all of them to character strings instead. When this happens, go in and investigate your data, apply the fix, save your data, live happily ever after. And I think another moral of the story here is that if you're designing a survey, try to design it with some resilience in place. People do things like this all the time. You tell them, enter your email address, and they'll enter something that doesn't look like an email address at all. And that's why if you've recently filled out a form where an email address was asked and you tried to fake it by not giving your email address, but just a random character string, it probably had what we call input validation, where it told you, hey, this doesn't look like a real email address. Please give me a real looking email address. So what's happening there is that it's not checking to see if your email address is real. It's just looking to see, is there like an @ in it? Is there maybe something.com or .edu at the end of it? So it's checking for certain characteristics of the text string you enter. So if we had done better with our cat lovers survey, we probably would have asked that question about the number of cats in a form where it asks you for validation. And if the user tries to enter in data that is not a number, it says, hey, this is not a number, please enter a number. So now that we have a good motivation for learning about data types in R, let's actually go ahead and learn about data types in R. So there are a variety of data types in R, and we're not going to focus on all of those, but we're going to call out 4 of them: logical, double, integer, and character. Logicals are what we call Boolean values, so they take on true or false. So if I was to, the function that I can use to inspect the type of a variable is called type of. So the type of the value true is logical. Character strings are always denoted by quotation marks in R, and it could be a single or a double quote. Both of them work. I tend to use double quotes. That's what the style guide we're following uses as well, but you can use single quotes. And so the type of this character string is basically character. Double and integer are both numerical data. So doubles are floating point numerical values, and those are the default numerical type in R. So these can actually take on decimal places as well. So type of the number 1.335 is double, but also type of the number 7 that doesn't have decimal places is also double by default. Now integers are indicated with an L. So type of 7L, if I want to say it's if I want to indicate that it is an integer, I have to do that explicitly, and then I get integer as a result. The reason why you might want to distinguish between the number 7 that maybe could have had a decimal point but happens to not, or the number 7 that's an integer, is that how we would model these data using statistical techniques is different. So that is one reason why you might want to make a distinction between doubles and integers. Am I trying to model how many cats people might have, in which case decimal points doesn't make sense, or am I trying to model people's ages, in which case decimal points make sense, even though people might report that number as whole numbers. Another place where integers come into play is if you ask R to give you a sequence of numbers, so give me everything between 1 and 3, it's not going to try to enumerate all possible decimal points, so it by default says you're probably trying to ask me for the integers 1, 2, and 3. Concatenation is what we can use to construct vectors in R. It's the C function that you've already seen in various places. So what I can say is if I want to create a vector with the numbers 1, 2, and 3, I can just separate them using commas with the C function. And this is what the result looks like. I can have character strings in there as well. Or I can have multiple vectors. So here's one vector that has the values hi and hello, and another vector that has the values bye and jello. And I can put them all together, and as a result, I get a vector of length 4 with values that were in the 2 separate smaller vectors that I concatenated together. The reason why we talked about this concatenation is what happens when you put things together in a vector, which is basically what we saw when we had data in a given column in a data frame. So when we're converting between data types, sometimes we do it with intention and sometimes not. So over here, if X is defined as the integers 1 through 3, so 1, 2, and 3, its type is integer. And if I want to say convert that to character for me, so I'm intentionally making this conversion, I use a function that starts with the word as. So this says take the X vector and give it back to me as character. So now I've saved that as Y. You can see that it looks a little bit different because now each of the entries are in quotation marks and the type of Y is given as character. If I have, let's say, another X that has the values true and false, so those are logicals as we've seen before, so the type of X is logical. If I want to convert that to numeric, R can actually do that because these logical values have a numeric definition as well, where true is 1 and false is 0. So R will happily convert a logical vector into a numeric vector. And then if I ask for this, the type of this new vector Y that I created, it gives me double, because remember that was the default numeric type in R. Now, R will also convert without intention, though, and that's what we saw earlier with the cat lovers example. So R will happily convert between various types without complaint when different types of data are concatenated in a vector. Now, whenever you hear, oh, something just happened and the person didn't even complain, that might seem like a good thing, but in this case, it's not always a great thing. So let's take a look over here. I have a vector with the number 1, and then the character string hello. If I put these together, because a vector can only have data of the same type in it, R just asks itself, okay, I have one number and the other one's a character string. Can I turn this character string into a number? The word hello doesn't really map to a number, so it says, okay, I'm going to go the other way. I'm going to turn the number into a character string. So overall, we get a vector that has two character strings in it. And so this going from the number that we had given it to the character string that it converted to is called type coercion. Here, I have a false and then an integer. And so what R actually does is it converts the false into a 0, because here the word false is not a character string, but it's a logical value, and it actually can convert to a numeric, which is 0. Over here, I have the numbers 1.2 and the integer 3. 1.2 can't be converted to an integer without loss of precision. So then it just says, okay, I'm going to make this 3 a 3.0 and give you doubles as a result. And finally, over here, I have an integer and then the character string 2. And basically both of them become character strings. And once you have this integer turned to a character string, you lose that definition of the L, because that's meaningless within a character string. We're not trying to say that's the letter L, it's just an indicator for that observation being an integer. So these are called explicit versus implicit coercion. So these are the formal names for what we've seen so far. Explicit coercion is when you call a function like as logical, as numeric, as integer, as double, or as character to intentionally convert the type of one variable from one thing to another. An implicit coercion happens when you use a vector in a specific context that expects a certain type of vector, and if it's not there, R will do the conversion for you. We'll do it quietly, and then you'll have to inspect the results to see if you're happy with the conversion that it did for you. What I would recommend you do right now is to pause the video and go to RStudio Cloud to work on the application exercise called Hotels and Data Types. There are 2 R Markdown files in there. One of them is called type coercion. So I recommend that you first knit that file. And then the question that we're asking you to answer is, what is the type of the given vectors? So you should first guess, then try it out in R. And if your guess was correct, great. But if not, think about why they have that type. So one example, for example, is suppose I want to know the type of this vector that has 2 elements in it. One of them is the number 1 and the other one is the character string A. So if I was working through this application exercise, what I would do is I would first check the types of these 2 elements. So type of 1 is a double and type of A is a character. Then I ask myself, what would I expect to happen if I put a double and a character together? And my guess is there's no way of going from the character to a number, so it must be that we're going to make the number into a character. So my guess would be a character. And so then I put them together and wrap them in the type of function to confirm whether my guess was correct or not. Some of these will be very similar to the examples we've gone through so far in this video, in which case I anticipate that you're going to think through them and get the right answer. And some of them are a bit trickier because they're using some of the examples we haven't really looked at explicitly here in the video. So I want you to think through why that conversion is happening the way it is happening. Before we wrap up this video, let's also talk about special values. So R has a few special values. Some of them are NA, which stands for not available, NaN, which is not a number, inf is positive infinity, and negative inf is negative infinity. So for example, pi, which is the number 3.14, so on and so forth, divided by 0. Whenever we divide a number by 0, it's defined as infinity, so R gives me infinity. 0 divided by 0 is not defined, so that gives me not a number. 1 divided by 0 minus 1 divided by 0, so that would be infinity minus infinity. That is not defined, so that's not a number. And infinity plus infinity is still infinity, so that gives me infinity. So you can use kind of like mathematical tests to see, to kind of guess what the results will be. And oftentimes your intuition will line up with what R is doing. Except when we come to NAs, things work a little bit differently because they are such special snowflakes. So let's take a look at this example that will feel familiar. I have a new vector called X, and I'm creating that vector by concatenating the numbers 1, 2, 3, and 4, and then an NA. So the fifth observation is missing. If I just try to find the mean of it, that gives me an NA because it doesn't know what to do with the NA value that I had. But if I explicitly tell mean to remove the NAs with the argument NARM set to true, then what R actually does is it sets that aside and finds the mean of the remaining values, so of the 4 values only, and that's 2.5, and that's what we're seeing here. The summary function, on the other hand, handles NAs under the hood without you having to say something. So it will calculate the mean with NAs omitted, and it reports the number of NAs for you. So there is some mismatch between how the mean function works and how the summary function works. And to be perfectly honest with you, there's not a great logical reason why that is the case. That's just how they've been implemented. So what you'll see is that when you have data that has NAs and you're trying to do something with it, how you do it depends on what you're trying to do and how the particular set of functions you're using have been implemented to handle NAs or not. The functions in the tidyverse tend to handle NAs all in the same way. I'm trying to think like maybe there's 1 or 2 exemptions to that, but generally they try to be very principled. But once again, coming back to the fact that the variety of packages in the R ecosystem contributed by thousands and thousands of package developers don't all handle NAs in the same way. And even functions that are in base R, like mean and summary, don't necessarily all handle NAs in the same way. So you simply need to get used to what's going to happen. But when you run a function and you get an NA as a result, the first instinct should always be to check, oh, I wonder if I have NAs in my data, and I wonder how this particular function handles that NA, and I wonder how I can get around it. NAs are actually defined as logical values. So if you look at the type of NA, you can see that that is logical. And that particular piece of knowledge can be helpful for thinking through how NA behavior is going to happen. So let's try to think about a mental model for NA. So unlike NaN, which is not a number, NAs are genuinely unknown values, and that's why they have a special place when we're working with data where missing data might be an issue. But that doesn't mean they can't function in a logical way. So let's think about why NAs are logical. Let's take a look at these. Why do the following give different answers? So remember this operator, the vertical line was an OR. So if I was to say, is something true or is it or NA? The result is true. But if I say, is something false or is it an NA? The result is NA. Why might this be the case? So I'll ask you to maybe pause the video for a second and try to think through this and then come back. So let's think through why these two gave different answers. NA is unknown, so it could be true or it could be false. So in the first scenario, the statement we were trying to work through was true or NA. So if NA was true, this basically would mean we're asking, is true or true, in which case the result is true. If NA was false, we would be saying, is it true or false, in which case the result would again be true. However, on the other side, if we're looking at false or NA, the result will actually vary depending on what value NA takes. If NA was true, then the statement we're looking at is something false or true, since we already have the true in there once, that gives us a true. If NA took on the value false, though, then we would be looking at false or false, in which case we would have false as the result. So since in the second scenario of false or NA, the value of the result depends on the value NA would have taken, if we knew what it was, R can't report either one of these for us and says, well, I don't know. This is missing information for me. But in the first scenario, where regardless of the value NA took, the result would have been the same, R happily then reports the true value for us. This doesn't really make sense for mathematical operations, this handling of NAs, but it does make sense in the context of missing data. So that's why R has this special value called NAs that are specifically for missing data that's different than the not a number, which is more of a mathematical construct, and why they behave differently and why various functions of working with data need to handle these NAs differently. And most of the time, you as the person who is working with the data and knows about the data need to be explicit about how you want your NAs to be handled.